This video is going to serve as a review of enols and enolates before we get to today's big topic, which is enolates and enols in substitution reactions. There are four main points that I'm going to make in this video. One, ketones are in equilibrium with the enol. Of course, the equilibrium constant is less than 1, spoiler alert, but they're in equilibrium. And we want to know the mechanism in both acidic and basic conditions. So we will review that. Two, enols can be treated with a base to form the enolate. That base can deprotonate and form the enolate. Or if you're under basic conditions, the ketone can go directly to the enolate. Three, if you have a ketone that has two different alpha carbons, it can make two different enols or enolates. And then four, a more substituted enol is more stable than a less substituted enol. We're thinking about alkene stability. Okay, so let's get started. Let's start by reviewing some terms and vocabulary related to today's topic. So you should pause and try to define in words and use a diagram to represent these terms. The carbonyl refers to the carbon-oxygen double bond, and there can be a variety of different substituents bonded to the carbon of the carbonyl. For example, if we have a hydrogen atom and then some alkyl group, R, this functional group is called an aldehyde. If you had the carbonyl and an hydrogen and then some amino group, this would be called an amide. So as you know, there are many different carbonyl containing functional groups. Today we'll talk primarily about ketones. So for ketones on the carbonyl, you have two alkyl groups, R. Now those R groups can be the same. So when R equals R, we say we have a symmetrical ketone. And when R is different than the other R, so for example, you have R and R prime, then you have an asymmetrical ketone. All right, let's look at some specific terms here. So let's take a look at the alpha carbon versus the carbonyl carbon. I have mentioned many times that the alpha carbon for a given functional group, it varies from functional group to functional group. So the carbonyl carbon for a ketone is the one bond, double bonded to oxygen. The alpha carbon, that is adjacent to the carbonyl carbon. For example, if we had this asymmetric ketone, right, it has two different R groups, you have two different alpha carbons. We know enolates and enols, and enolates looks like this, for example. An enol looks like this. En, that's the double bond part. The enolate is an anion. Enol, we have the en, and then you have an alcohol, the ol. We have thought about the relative stabilities of enols and enolates. So imagine you took this asymmetric ketone, so you took methyl ethyl ketone, aka, sorry, I shouldn't have said it that way, it's 2-butanone. So if you take 2-butanone and deprotonate the two different alpha carbons, there are two possible enolates. So how can we consider their relative stability? Well, it's with the en part. So we have a tri-substituted alkene versus a di-substituted alkene. And so the tri-substituted alkene is more stable or lower energy. Remember, when we consider alkene stability, we're thinking about the 2 carbons of the double bond, and each of those carbons is bonded to 2 groups. And then you're thinking about how many of those groups are not hydrogen, are alkyl. So the more alkyl groups, the more stable. Excellent. Let's keep going. Now that we've reviewed these key terms, let's practice identifying the alpha carbons for each of these carbonyl compounds. Please then draw in any implied hydrogens on those alpha carbons. Last chance to pause. So this first molecule has 2 alpha carbons. This alpha carbon has no alpha CHs, but the other one has some alpha CHs, so it has 3 of them. Excellent. Next, again, we have 2 alpha carbons. This time they both have CHs. And we can call them alpha and alpha prime when they're different. We'll go ahead and do that. Next, well, this is an aldehyde, and it has 1 alpha carbon, but it has no CH on it. Right, this carbon is making 4 bonds already to other carbons, so there are no implied hydrogens there. And then I will point out that the hydrogen of an alpha carbon, this is not acidic. Do not deprotonate it ever. So you just can't make an enol or an enolate of that aldehyde. So there will be no enolate possible for that aldehyde because there's no alpha CH. And the aldehyde CH, the one bonded to the carbonyl carbon, it is not acidic. Awesome, so here's another aldehyde. It only has 1 alpha carbon, and we'll go ahead and draw its alpha hydrogens in. And then for this last molecule, we have 2 alpha carbons. They're different, so let's go ahead and call them alpha and alpha prime. Each of them has alpha hydrogens. Good. Let's consider acetone in this question. What will happen if we treat acetone with 1 equivalent of a strong base? And we can imagine that this strong base can deprotonate whichever the most acidic proton is for acetone. Now, of course, acetone only has 1 type of proton. It has these protons. So I'm going to draw 1 out because we need to deprotonate it. We're going to show the curved arrows, but all of these protons are the same. So we don't really have a choice here. So we take the base, we're going to deprotonate, and we might put the electron pair on carbon like this. Excellent. Okay. Oops, it's neutral. So now we have the conjugate base and the conjugate acid from that proton transfer reaction. All right, let's go ahead and copy this because we're going to think about this molecule. So how can we think about the stability of this conjugate base? Yeah, well, hopefully you have recognized that it can be described by resonance structures. So this lone pair can actually be shared between this is the alpha carbon and the carbonyl carbon, and the pi electrons can go to oxygen. Let's go ahead and show all the lone pairs here too. So when we do that, when we share the electrons in that way, we end up with this structure. Do you recognize this structure on the right? Yes, this is what we refer to as the enolate. So let's make sure we understand like what my point is. So here's my point. When we deprotonate acetone, which is a ketone, with a strong base, it generates this conjugate base. We now have realized that that conjugate base is an enolate, which we're familiar with. Now, which of these resonance structures is more stable? The one where you have the negative charge on carbon or the one where you have the negative charge on oxygen? Yes, it's the one where the negative charge is on oxygen. So this is the major resonance contributor. You will find that moving forward in this class, when we draw curved arrow mechanisms, we want to draw them directly to the most stable resonance structure because the enolate is really not it's not best described by this resonance structure. It's best described by this one. So in general, we want to draw our curved arrows to go directly to the major resonance contributor. So let's try again. And this time I really want you to pause and try and draw the curved arrows for the treatment of acetone, which is going to act here as an acid, and this strong base to form the enolate, which is the conjugate base of acetone, and then the conjugate acid of the strong base. All right, draw in the curved arrows here, and you want to go directly to this resonance structure. Don't stop at this one. Go to the major one. Well, we do need to draw out the acidic hydrogen. So here we go. This lone pair of electrons accepts or attacks sigma star CH. Filling an antibonding orbital breaks a bond. So we want these electrons, they're going to go make the pi bond, right? We see that these electrons are making a pi bond in the product. The electrons from the base that we use to do the deprotonation, these electrons, they're making the BH bond. And then finally, this will break the pi bond. And those pi electrons, I'm so used to implying my lone pairs, they're going to show up on the oxygen, giving it that negative formal charge. So go from 2 lone pairs to 3 lone pairs on oxygen. Good. So I want you to practice this. In the textbook, they do not always go directly to the major resonance structure, but that's okay. I would like you to try to do it. So you're going to see me. I'm always going to go directly to the enolate when I deprotonate to form an enolate. The enolate resonance structure that's most stable and has the negative charge on oxygen. So we're going to practice that. So let's consider enolates. They are described by 2 resonance structures, as we've been discussing. They're described by the resonance structure that has the negative charge on carbon and described by the resonance structure that has the negative charge on oxygen. We know that this resonance structure is more contributing. Enolates can be bases and enolates can be nucleophiles. And because they're described by 2 of these resonance structures, they can actually react in either position. So what does that mean? That means that the lone pair can react, imagine it reacting from carbon, or it could react from oxygen. It can react from either atom. So this is called ambident. It's an ambident nucleophile. It has 2 electron-rich sites, which is the title of the slide. And this make an analogy to water. Water can be acidic or basic, so it's called amphoteric. So an enolate can react at 2 different positions, and so it's an ambident nucleophile. So let's show the products from protonation, so reaction with a proton, at either of those electron-rich sites. And let's see if we recognize them. So if we protonate the alpha carbon, we will end up with what? Yeah, the ketone. If we imagine protonating at oxygen, we end up with what? Yeah, the enol. And of course, what do we know about ketones and enols? Yeah, they're actually in equilibrium with one another. Can you recall which side of this equation is favored equilibrium? Yes, the left side. So for most ketones, the equilibrium constant is much less than 1. And this is primarily due to the CO double bond being stronger than the CC pi bond. That's the primary driving force or reason why the ketone is favored at equilibrium. But we do see that most ketones are in equilibrium with their enols under both acidic and basic conditions. Let's quickly review the mechanisms for the tautomerization under acidic and basic conditions. There's a couple main things that need to happen here. So we need to remove the alpha CH. So it goes from CH3 to CH2. When we do that, we also generate the pi CC and lose the pi CO to make a single bond CO. We also need to add or protonate OH. So there's two main steps because these two sort of go together. And then which one happens first really depends on whether or not you're in acidic or basic conditions. So under acidic conditions, you're going to protonate first, which means that you're going to make OH first. So let's take that basic pair of electrons or that electron-rich site. It's not all that basic, but it's basic enough, and protonate. Under acidic aqueous conditions, the acid is hydronium. The acid in species, or the acidic species in solution is hydronium. Cool, so now we have made the OH bond. We just need to deprotonate, remove the alpha CH bond, which makes the pi CC and breaks the pi CO. So the protonated carbonyl, this is acidic. This is the acidic solution. Again, in acidic aqueous solution, the base will be water. There's no hydroxide. Don't try to force it. All right, excellent. So that gets us to the enol. So that's under acidic conditions. Now, under basic conditions, we have acidic conditions, you protonate. Under basic conditions, you're going to deprotonate. So the first thing is to deprotonate the alpha carbon. Under basic aqueous conditions, the base is hydroxide. So we're going to deprotonate that alpha carbon, make the pi CC, break the pi CO. That generates the enolate. And then the enolate, just like we showed not too long ago, right here, the enolate can get protonated to form the enol. The acidic species in basic aqueous conditions is water. I hope this all sounds familiar. I have this summarized on this next slide, and this can be scary sometimes. I'm not going to go through this, but this is typed out what we just wrote together, and it's here for your reference. Now that we've reviewed that ketones are acidic at their alpha carbons, we're going to show the enolates that will result from deprotonation of the most acidic proton in each of the following species. So the most acidic proton is going to lead to the thermodynamic product in this case. That's what I mean in this case. And for enolates, we are thinking about the most substituted double bond. So these are the same molecules that you analyzed back at the beginning of the lecture. So you've already analyzed their alpha carbons. You know which ones have acidic hydrogens and which ones do not. So you might refer to this slide. Okay, so for our first ketone, we have these two alpha carbons, but only this one actually has hydrogens on it. So we would deprotonate there. I'm going to abbreviate the ring as phenyl, just so I have enough space. Okay, and so we would have this enolate. That's the only option. Now the next one, we do have two different alpha carbons. So we have to decide which one to deprotonate. We're going to deprotonate at the tertiary carbon because that will generate a more substituted double bond than deprotonating here at the secondary carbon. So what we'll end up having is this enolate, not the other one, which I'm going to draw super tiny because we don't see it. So not this one, because it would be tri-substituted versus tetra-substituted. So we're going to see the tetra-substituted one. Excellent. Let's just keep going left to right here. So for the aldehyde, we already discussed here, there are no alpha CHs, so no enolate is possible. All right, let's go over here. So for this aldehyde, it only has this one alpha CH. Again, the aldehyde hydrogen is not acidic. So if you deprotonate at the alpha carbon, you will obtain this enolate. Excellent. Last one. So for the last example, we still have two different alpha carbons. We have one of them is secondary, one of them is primary. We have said that for this question, I'm looking for the most stable enolate, the most stable double bond isomer. And that would be this one from deprotonation at the secondary alpha carbon. Okay, so this one is going to be more substituted than deprotonating at the primary carbon. We're going to look at some enolates and enols in action today. So this is the first reaction we'll look at, and it's called a deuteration reaction. Deuteration really just means replacing hydrogen atoms with deuterium. Deuterium is the common name, the fancy name for the hydrogen 2 nucleus. So where the hydrogen has one proton and one neutron in its nucleus, versus the more naturally abundant isotope of hydrogen, which is the H1 nucleus, which we just call hydrogen. So this is just a deuteration. You're replacing the H1 nucleus with the H2 nucleus, so with deuterium. So let's take a look. We are in basic conditions. So if we're in basic conditions, then we're going to deprotonate. If you think about where to deprotonate, it's very clear you're breaking these CH bonds and you're making the carbon deuterium bonds. The CH bonds that you're breaking are on alpha carbon, so that's super because we know how to do that. So let's go ahead and do that, and we'll deprotonate the alpha carbon on the right, but it does not matter. So we start out with this proton transfer reaction, and that generates an enolate. And again, you do want to directly generate the most stable enolate. Cool, we have broken a alpha CH bond. Now we need to make an alpha carbon deuterium bond. So how do we do that? Well, this is the second step, sort of going in reverse for enol keto tautomerization. So we deprotonated it. We're basically doing the reverse of this step. We're going backwards, but instead of instead of protonating, we are incorporating deuterium. So we're going to use the D2O for that. And we can see that we have incorporated one of the deuteriums into the molecule. So now how do we generate all of these other bonds? This one, and this one. How do we break those bonds and make the carbon deuterium bonds? Exactly the same way. So we're going to use the deuterium version of hydroxide because that's the base that we have around. That generates this enolate. Now, if you're wondering, hey, why did you deprotonate hydrogen instead of deuterium? Well, because that's what gets me to the product. But yes, you would deprotonate either of these or either of those. All of that happens. We just have to take it one step at a time. And then again, we're going to protonate with D2O, and that generates this species with now 2 deuteriums incorporated. And we would just repeat for these 2 protons to get the products. So a couple of things that I'll point out here is that when you're under aqueous basic conditions, the base is going to be hydroxide, or in this case, the deuterium version of hydroxide. And the acid is water, or in this case, the deuterium version of water, which is D2O. Okay, we're going to try the same reaction mechanism now. Well, same transformation, but we're going to look at it in acidic conditions. So this time we have the deuterated version of hydronium and the deuterated version of water, and it's the same overall transformation. We've deprotonated the alpha carbon and replaced it with deuterium. Under basic conditions, we deprotonated first. Under acidic conditions, we're going to protonate or deuterate first. And I'll point out one more thing. So under basic conditions, we went by the enolate, right? So in basic conditions, we observed the enolate. What do you think that we're going to observe in acidic conditions? Yeah, we're probably going to observe the enol. Let's go ahead and just actually, you should pause and try this yourself. Last chance. Okay, so we're under acidic conditions, we're going to protonate something, and really your only choice is that non-bonding pair of electrons on oxygen. Excellent. So now that we have the protonated carbonyl compound, then we can break the alpha bond, the alpha CH bond. You do not try to directly break these bonds because this is not acidic enough to do that under these conditions. And that's because we don't have hydronium anymore. We don't have the deuterium version of hydronium. The base that we have under aqueous acidic conditions is water. In this case, it's the deuterium version of water, D2O. So now D2O can deprotonate at the alpha carbon, make the pi bond, push these electrons up. Yeah, okay, cool. So we can see we're generating the enol here. We removed one of those CHs on the alpha carbon that we know has to go away. From here, what do you think happens? Yeah, this is electron rich. You have an acid, you have the deuterium version of hydronium, and so you can make that carbon deuterium bond that you see clearly in the product. So this mechanism is probably a little bit more challenging for you, I would guess. But you just need to ask yourself at every step, do I have an acid? Do I have a base? Okay, this is very acidic. So we could just deprotonate on deuterium, or excuse me, on oxygen to relieve that positive charge. So we could definitely do that. But look, make the parallel to the protonated carbonyl over here. You could deprotonate the deuterium, or you could deprotonate the alpha carbon. Both of these options are going to relieve that positive charge on the oxygen. But if you deprotonate at the alpha carbon, that's also going to help you to um, incorporate the other deuterium atoms. You're going to make the enol. So let's break this bond. And then that gets us to the enol. We remove that hydrogen. Again, if you're asking why did I choose to remove hydrogen and not deuterium, just because that gets me to the product. Okay, and then now we have our electron-rich enolate, or enol in this case, and then that can react with another molecule of the deuterium version of hydronium, and this will get us all the way to the product. So you can write out this full mechanism if you would like. I will try to remember to put it in the... You may recall learning about a molecule called the litamide. The litamide is a chiral molecule. Both enantiomers are drawn here, and the stereogenic center is indicated by the star. Now, this molecule was discovered as a pharmaceutical agent in the 1950s. When its biological activity was studied, they realized that it was effective as a sedative and an antiemetic agent, meaning that it helps with nausea. Because of that, it was widely prescribed to pregnant women in Europe to help with their morning sickness. Now, unfortunately, at the time, they did not realize that the S enantiomer had different biological activity. It was a teratogen, which means that it causes damage to a fetus. Now, in particular, the S enantiomer of the litamide causes what is referred to as limb bud apoptosis. Now ask yourself, what is limb bud apoptosis? Well, apoptosis means cell death. And what do you think a limb bud is? Well, it's the developing limb of an embryo, of a fetus. So many children were born in Europe with underdeveloped limbs or missing limbs. This story is a victory for the United States FDA because they refused to prescribe it because they had felt like its safety had not been fully tested. And there's actually a statue of the head of the FDA at that time now in front of the FDA building. So, what is the bottom line here? Well, at the time, you all already know that enantiomers can have different biological properties. It's the normal handshake and the awkward handshake, right? Enantiomers have the same physical properties, except how they interact with other chiral substances. Now, this could only be made as a racemic mixture at the time in the 1950s. Today, there are techniques to just simply make R-thalidomide. But even if you could get R-thalidomide in a bottle, it turns out it still cannot be safely administered to anyone who is pregnant or expecting to be pregnant. And that is because it racemizes in the body. Racemization, again, means that you start with an enantiomerically enriched species, so say one enantiomer, and then end up getting a mixture of enantiomers. So under physiological conditions, the ketone form will be in equilibrium with the enol. And then let's think about what's happened here. So I'm gonna abbreviate this. So think about what's happened here. You destroyed, or we've destroyed, it has been destroyed, the chiral center. Now this is flat. There's no more chiral center. Do you see how this is an enol? It's an enol in a very weird context, I know, but it's still an enol. So there's no more chiral center. And then when this reacts to go back to the keto form, which is the litamide, protonation could occur to the top face. If it occurs to the top face, you form acetylalitamide, right? Proton on the top face, protonation of that carbon on the top face. There's the what used to be the stereogenic center. Or protonation could happen to the bottom face and you would get the R thalidomide. And of course, it's a 50-50 chance what's going to happen because the top face and the bottom face are the same. So even though today you can make R thalidomide, if you cannot administer it to pregnant women because in the body it will racemize to make the mixture of the R enantiomer and the S enantiomer. I will say this is still used as a drug today to treat multiple myeloma. However, it is not given to pregnant women. Excellent. So all of these examples, so the racemization of thalidomide, the super weird deuteration under acidic, basic and acidic conditions, they all help us practice achieving our goals, which are to think about enol formation, enolate formation, and then how, like, what sorts of reactivities ketones can have because of the fact that they're both in equilibrium with the enol. And if you just treat them with a base, you can make the enolate. And enolates and enols, they do stuff. They're nucleophiles or they're basic, like they do stuff. So we're going to get into some more interesting stuff now that you've reviewed.